All right, happy Halloween, everybody. Y'all being everybody's costume is a student costume today. All right, so y'all had your exam, right? Uh, Anybody have issues? Everybody got the exam done? I know it's like it kicks you out and stuff. It's like trying to prevent you from cheating. It doesn't want you to like look at the book, online book, or switch web pages. So like when y'all are taking the test, I just sit there at my computer and like every 2 minutes, I keep re-enabling access for everybody over and over and over again. All right. So I don't know if anybody like got unfairly kicked out. Like if you have like bad internet or something, or your computer crashes, it, like won't let you back in. So it's a lot of work on me trying to fix everything. But all y'all got to take the exam, okay? No issues. What about out there in Zoom land? Y'all get to take the exam, okay? If there's any issues, I want to address them. All right. I'm not going to do office hours today, right? It's Halloween. I have to get my daughter ready for Halloween. I will be going to my office right after class for a little while. So if you have questions, whatever, you can walk with me there. Um, so there you have it. I caught my daughter hiding in the bathroom in front of the mirror, practicing her different cries. Apparently, the terrible two is like start the day that they turn two. All right. Incredible manipulation. All right. So we have approval for everybody on the exam. Great. All right. So we are moving on to module, not a module, what are we? Chapter, how are we? 13, 13.1, 13.2, antiderivatives. This is going to be easy. It's just the opposite of a derivative. All right. There's a little notation, right? Not much though. So let's say we have, they like to use big F. So basically, we know the derivative of x squared is 2x, right? So we would say the antiderivative, over here I'll put the antiderivative, would be, the antiderivative of 2x would be x squared. So we're going backwards, is all we're saying. And the way we write that, we'd say the integral of 2x with respect to x is x squared. All right. So this is like the opposite of the derivative. It's the antiderivative. Okay. So the derivative of x squared is 2x. So the antiderivative of 2x is x squared. Does that make sense? Just going backwards. And think of this here as telling you which symbol or which variable, just like when you take the derivative, like that's the derivative of x, but with respect to what variable, we used to put dy dx. So this thing down here told you which variable to take the derivative with respect to. Remember, if you had the x's and the y's and the z's, you need that down there. But the dx by itself, this is the derivative operator. This tells you with what variable you're differentiating with respect to. This, the funny skinny long s, that's the integral operator or antiderivative operator, right? And this is telling you which variable you're taking the derivative with respect to. See, if I did dx, I can do this without, I took the derivative of both sides, right? This would cancel with that. This cancels with that. We have 2x equals the derivative of x squared with respect to x, which is 2x. So the symbols make sense. All right, and we're going to develop these symbols slowly. It's really, and there's one more symbol, constant. So yeah, we know the derivative of x squared is 2x, right? But we also know the derivative of x squared plus 1 is also 2x. We know the derivative of x squared plus 7 is also 2x, right? So what that says is the integral of 2x with respect to x is x squared plus any constant, right? So what is the integral of 2x? Well, there's an infinite number of them. X squared is one of them. X squared plus 1 is another. X squared plus 7 is another, right? There's an infinite number of antiderivatives, and they all differ by a constant. You can always add, because the derivative of a constant is 0, right? So here's another piece of notation, this plus c. It's hard to remember to put the plus c every time, but you need to have it there. All right, so I felt like hell all morning. Finally feeling a little better. They use this big F and little f because they don't want to introduce the integral symbol just yet, right? So they say if big F is 10x and f prime equals 10, then big F is the antiderivative of a little f. So all they're saying is the derivative of 10x is 10. So 10x is the antiderivative of 10. Basically, they're saying the integral of 10 with respect to x is 10x, right? Because the derivative of 10x is 10. Does that make sense? Okay. And then 5 to the 4th, all right? So if we want to take the integral of, let's see, how are they saying this? The integral of 5x to the 4th, this would just be x to the 5th plus constant. So if I take the derivative of that, I multiply it by the 5, subtract 1 from the exponent, and I get 5x to the 4th. Okay, does that make sense? All right. Here's where they introduce the plus c. They do it in a really roundabout way. So the same example I just did. They said, here's one antiderivative. It's x squared. Here's another one, x squared plus 2. Here's another one, x squared minus 4. The derivative of all of those is just 2x, right? So they say, look at the difference between any two antiderivatives, and you're going to get a constant, right? That's all they're saying. The difference between x squared plus 2 and x squared minus 4 is whatever, 6. So although there are an infinite number of antiderivatives, the difference between any two of them is just a constant. And best picture, here's a good picture. All right, so here's x squared minus 4, x squared plus 2x. The slope for all of these is 2x. The slope of this guy is the exact same as the slope of this guy is the exact same as the slope of this guy for any x, right? So that's why we add that plus c. So if we say, what is the integral of this? We'd say, well, it's x squared plus some constant. This plus c, all it's doing is shifting this thing up or down, okay? Does that make sense? It's all the constant does. And this will become important later, because later on, we'll need to actually solve for the c. And when you actually apply these equations and you want to use them, well, you can't just have some floating, like, what is that, plus $1 billion, minus $1 billion, right? It becomes important. So we'll see that a little while later. So here is where they introduce their little symbol here. All right, the integral of f of x dx, right? This is called the integral sign. The f of x is called the integrand, and the whole thing is called an indefinite integral. Here soon, in the next couple of sections, we'll do definite integrals, all right? So what this is really, if you think about it, this is your y value, and this is a change in x. Let's say we have let's say here is f of x, right? Right? So for any x value, I'll call this like x sub I. Well, and then I'll make a little rectangle here. Bust this thing into rectangles. And I'll call this little, like the length here, I'll call that dx. So each one of these rectangles has a width dx, okay? They're all the same. What's the height? The height of this would be f of whatever that is, xi. So each one of these x values, you plug it into the function and you get a different y value, right? So the area of each one of these, the area of that rectangle would be f of whatever this x is times the width. So all this is width times height. This is the area of a rectangle. So what they're doing here is this is the width, this is the height, this is the area of a little rectangle. All right. So what this integral symbol is it's the area underneath the curve. That's what this thing gives us. Okay. And so if you look at this though, there's error there. Like what about like this blue mark? Right? These rectangles aren't taking into account this little bit of blue. Right? So there's an error. So what we do is we say, okay, well, let's let the dx here get even smaller. If I let the rectangles get smaller, if I have smaller rectangles, then there's less blue, right? So there we go. I get rid of the error if I make my rectangle skinnier, right? So all we do is take the limit of the width of the rectangle, let it get infinitely small. So what we are doing is we are summing up the areas of all these rectangles. So what we end up with is an infinite number of rectangles that are infinitely skinny. Does that make sense? That's why it's a sum. It comes from this symbol, which is for sums, right? And that's where the symbol comes from. So all this is height times width, an area. Now, this is called an indefinite one because we don't, a definite one, we would have numbers here. We might say from 2 to 4, right? So if here's 2 and here's like 4, we'd only be looking at this area, right? So if you put numbers there, the output is a number. If you don't put numbers there, the output is a formula for the area for any interval, right? So if you have something like you could say, what's the area from here to here, right? Or you could say, well, what's the area from here to here, right? You get different areas, right? But in general, this is just going to be a formula that's going to tell you what the area is from any 2 points, right? And there's also a relationship. I've mentioned this before. The area of a circle is pi r squared, right? The circumference is the derivative of the area is 2 pi r, right? So here's a circle. The derivative of the area gives you the boundary, okay? The volume of a sphere is what? Forget 4/3 pi r cubed. So the volume prime would be the surface area, which would be 4 pi r squared. So take the volume inside of a sphere, take the derivative of that, and you end up with the surface area of the sphere. Or if you have the surface area, you could figure out the volume by taking the integral or the antiderivative. Okay, so these you know what? Every time you take if you take a derivative, right, you end up with 1 power less, right? Remember the power rule? You end up with 1 less dimension, right? If you start off with a volume, right, and you take the derivative, you end up with an area, right? And so the relationships between antiderivatives and derivatives hold in all dimensions. So this allows you to bounce between 12 and 13 dimensions. It's called like surfaces and hypersurfaces, or volumes and hypervolumes. It allows you to bounce between dimensions, all right? But we're not going to get into any of that in here. I just want to give you a glimpse of some of the coolness of math. They call this the indefinite integral. And then 2 or 3 sections, I guess we'll be doing definite integrals. Now, y'all know how to take derivatives. Derivatives are easy, right? There's like 4 rules. Power rule, the product rule, the quotient rule, and the chain rule, right? That's it. All we're doing is the same thing backwards, right? So if I want to take the integral of x to the 4th, this would be x to the 5th over 5. Right? Because if I take the derivative of this, the derivative of a constant is just 0. Take the derivative of this, I'd have to multiply it by the 5, which would cancel with that one, subtract 1 from the exponent, and I get x to the 4th. All right? So the first thing we learned was how to take the derivative of stuff like this. So we're going to start with the antiderivative of stuff like that. So instead of subtracting 1 from the x, we multiply it by the exponent and subtract 1. So if we're doing this backwards, we're going to add 1 to the exponent and divide by it, right? Instead of multiply by the exponent and then subtract 1 from the exponent, we do the exact opposite in opposite order. Add 1 to the exponent and then divide by it. The exact same thing we've done over and over and over again, just in reverse order. Does this make sense? So if I have the integral of x cubed, all right, I'd add 1 to the exponent and divide by it and add a constant. So the derivative of this is that. And that's derivative, that's just 0. All right, and we could do that for anything. So what we want to do is write a general formula. Remember we used to have, well, the derivative of x to the n, we would have n x to the n minus 1. We had this like, here's the generic formula for the power rule for taking derivatives for any power n, right? But we want to write down the same thing for integrals. We'd say x to the n dx. Well, I'd have to have 1 higher on the exponent, and I'd need to divide out that exponent and add a constant. See, if I took the derivative of this, I'd multiply by the exponent, cancel that, and then I'd subtract 1 from the exponent. Instead of n plus 1, I would have n. So these are saying the same thing. One's talking in terms of antiderivatives, one's talking about derivatives. But all this is the power rule. All right? I know there's n's and symbols and stuff, but it's not complicated. We're just doing the power rule backwards. There it is. Power rule for antiderivatives. Right? And we could check, right? The derivative with respect to x of this guy, right? 1 over n plus 1 times x to the n plus 1 plus a constant. The derivative of this would be n plus 1, subtract 1, and then derivative of the constant is 0. This is just 1 x to the n, right? Applying the power rule. Let's do some examples. For x to the 5th, we need an x to the 6th over 6 plus a constant, right? Multiply by the 6, subtract 1, we get x to the 5th. This is the same thing as t to the minus 2, right? So we'd have to have 1 higher on the exponent, and we'd need to divide by that exponent. If I multiply by the minus 1, those go away, and then subtract 1, I get the minus 2. The rest is arithmetic, making it pretty. Of course, we want to write this as negative 1 over t, right? All right, this is u to the 1/2 du, right? So we would have to have 1, add 1 to the exponent, divide by the exponent. Make sense? If I took the derivative of this, I'd multiply by the 3/2, subtract 1 from the 3/2, I get 1/2. course, we'd want to rewrite this as 2/3 u to the 3/2 because this just looks stupid, having a fraction on the bottom of a fraction, right? This one, they tried to make it so simple that it would be confusing. This and this are opposites of one another. The little d means derivative. The big S means antiderivative. The antiderivative of the derivative, they undo one another, right? It's just x, right? What's the derivative of x? It's the derivative of x, right? dx. That's simple, right? How can I write this? Derivative of x squared, that we know is 2x. If we move this over here, boop, then we integrate both sides, boop, boop. The integral and the derivative here cancel one another out. We have the integral of 2x dx is x squared. That makes sense how the symbol will work here. I mean, I know y'all are used to having like d dx, that's the operator, right? Well, d by itself is an operator. This is like an addendum to that operator. It tells you what you're differentiating with respect to. Okay? Remember, the lowercase d is just change in, but this thing here means sum. We're summing over a change in something. Okay? So the symbols do make sense. I want y'all to like not just memorize it, get the answers, but get a little bit of intuition too, you know. But none of y'all are going to take multi-variable calculus, so it's all right. So let's look at these. This one, we would have an x to the 7th over 7 plus a constant, right? Take the derivative, the 7's cancel, subtract 1 from 7, and you get the x to the 6th. This is 1/4 power, right? The fourth root, that's x to the 1/4. So I would need to have x to the 5/4 plus a constant, right? If I took the derivative of this, the 5/4 would cancel, subtract 1, and I would get the 1/4 power, and I need to have my plus a constant. This one, this is just 8. I'd have to have 8x. The derivative of 8x is 8, right? Okay. This just says you can do exactly what you think you should be able to do. All right. Just like derivatives, you could take a constant and pull it out front, right? So like if you had 2 times x cubed and you're taking the derivative, you could pull this 2 out, right? And the integral of a sum is the sum of the integrals. So that's nice as well. All right, so it says you could do what you think you should be able to do. There's no problem with that. Now, what you cannot do is this. You cannot take this x and I'm just going to pour it out front. No. This thing and this thing is the boundaries. Anything that is an x or a function of x has to stay in between here, all right? Just like you can't be like, oh, if I had like x times square root of x plus 1. You can't just take this x and just pull it out and be like, I don't care about that x. You can't do that, right? Cannot do that. You pull constants out. So let's look at some examples. So they said you can just pull that 4 out. All right, so we have this 4 here. Now the integral of x to the 7th would be x to the 8 over 8. This here is the 10. I can pull the 10 out. I'll rewrite the z here. So I have the 10. The integral of z to the minus 6 would be z to the minus 5 over minus 5. Right? Product rule backwards. So. All right, so this guy we would say, well, I could pull the 5 out. And the second one, I could pull the 6 out. And then the last one, I could pull the 2 out. Notice there's parentheses here. dy is being multiplied by everything there. So there's a dy for each one of these. All right. So for this one, I would have a 5. The integral of y squared is y cubed over 3. And I have a minus 6. The integral of y would be y squared over 2. And I have a 2, and the integral of dy is just y. I add plus a constant. Same thing over and over and over and over again. So you can do it reflexively. Look at all these. I can pull out the minus 6. The x to the 8th would become an x to the 9th over 9. This one, I could pull the 7 out. See, if I add 1 to 2/3, that would be 5/3. I could pull the 5 out. This is really x to the minus 3. So I'd have to have x to the minus 2 over minus 2. All right. I took the derivative, multiply by the minus 2, subtract 1 from the exponent. I would get that. Right. This guy here, I would pull the 5 out. The x to the 4th would become an x to the 5th over 5. Then I'd have a minus 3. The x squared would become an x cubed over 3. And then the 8 would just become an 8x. The derivative of 8x is 8. And then I need plus a constant. All right, here I have a 4. This is x to the 1/3 power. So if I add 1 to 1/3, I get 4/3. Here I have a 2. This is x to the minus 2, so I'd have to have an x to the minus 1. Y'all getting it? It's done like the exact same thing like 900 times. All right. All right, this thing, I'd look at it and be like, no freaking clue, right? But I can simplify this, right? What is x squared over the square root of x? What's x? This is x to the minus 1/2, so this is x to the 3/2, right? So I would take that and rewrite it as x to the 3/2, and then that would be x to the minus 1/2. So for the first one, I would have to have add 1 to 3/2, 5/2. Add 1 to minus 1/2, that'd be a positive 1/2. Add a constant. And of course, do the arithmetic to make these pretty, right? Something like that. Like the answers be pretty. That's 1, 2, 3, there's another one. So if I just looked at this and thought, okay, derivatives are easy. There's product rules, power rules, chain rules. If I looked at this and just tried to think it through, I'd be like, well, I need to find something. If I took the derivative of it, that would give me that. I'd be like, well, I would need this, right? Because if I took the derivative of that, I'd multiply by the 3's, I'd subtract 1 from the exponent, and that would give me the squared. But dang it, if I took the derivative of this, I'd also end up being multiplied by a 2x, right? because that chain rule stuff. So this won't work. If I put a 2x under there, so that that's not going to work. So now I got to use the quotient rule, right? So looking at it like this, it's like I have no idea what the integral is. I don't know what I'd take the derivative of to get that. But if I square this dude out, I got an x to the 4th minus 2x squared plus 1. And now it's easy to do. This guy gives me x to the 5th over 5. This guy gives me an x cubed over 3. And the integral of 1 dx is just x. So there's the integral. If I took the derivative of this, I would get that. Doesn't look like it, but it is. It's true. Right? So this is what makes integrals much more difficult than derivatives. Even though derivatives are really easy and you're just doing it backwards, right? You think, shouldn't it be easy to do something easy? Shouldn't it be easy to do backwards, right? Like saying the alphabet backwards is not easy, right? Multiplying two numbers together is easy. Figuring out what factors is hard. It's easy to go from, well, it's easy to go from this to multiply x squared minus 1 times x squared minus 1. That's easy. But going from this to that is very difficult. And this is why all of our internet security works. They give you two huge prime numbers. Those are the keys. They multiply them together. So if you look at a huge number that you've been promised is the product of two prime numbers, and they ask you, okay, which two prime numbers did I multiply together to get this number? That problem is almost impossible. It takes like more time than the age of the universe and processing power to figure out which two primes multiplied together to get that number. But multiplying two numbers together is trivial. It's super simple, okay? So we have the same issue here. You're going to see that these examples have been simple, but here pretty quick, finding an integral, there's going to be an art to it. And that's most of physics, is figuring out how to take integrals of nasty looking stuff. Let's do these. All right, so this is really 1/2 minus 2. What's 1/2? That's minus 3/2. And then this would be x to the minus 2. So if I add 1 to minus 3/2, I'd have a minus 1/2. And if I add 1 to minus 2, I get a minus 1. All right, this dude, I'm going to square this thing out. The square root of x squared would be x, and I'd have 4 root x plus 4, right, if I square that thing out. So the integral of x would be x squared over 2. This is x to the 1/2, so I'd need a 3/2. And the integral of 4 would be 4x, and we add 1. Are we good? Am I going too fast? Okay. Before we go there, let's see, what is it? The integral of x to the minus 3, right? This would be x to the minus 2, right? The integral of x to the minus 2, well, that would be x to the minus 1, right? The integral of x to the minus 1 would be integral of x to the 0 divided by 0. Can't divide by 0. Right? When we were doing the power rule for derivatives, we never had any problems, right? You could always do the power rule, take the derivative, no problem. But doing the exact same thing backwards, you can't do the same thing backwards. Why is it that taking the derivative is so easy with the power rule? The power rule always works. But doing the same thing backwards, it doesn't. You end up dividing by 0. All right? So here's your first inkling that antiderivatives are harder than derivatives, even though they're the exact same thing, but in reverse. There's quirks. Remember the derivative of natural log Dang it. Was 1 over x, right? This is y, all right? So boom, right here, the integral of this is going to be natural log of x. Who knew that natural log of x is the same thing as x to the 0 divided by 0? I mean, what is this? This is 1 divided by 0. Natural log is not 1 divided by 0, is it? 1 divided by 0 doesn't make any sense. 1 divided by 0 is anything you want it to be, right? So, but before we get there, before we got into natural logs, we introduced exponential functions. So, in the spirit of following the same path, we're going to do exponential functions. Since the derivative of e to the x is e to the x, the integral of e to the x is e to the x. Makes sense, right? And remember, if you had stuff, if you had e to the stuff, the derivative was e to the stuff times the derivative of the stuff, right? So that means when you're taking an integral, if there's a number up there times the x, you have to divide that thing out. Just like you had to divide out the exponent whenever you're doing the power roll backwards, right? It's the same thing. You just have to divide out that k. Just take the derivative of that, you're going to get that, and then a k. And you want those to go away. All right, so here they work them all out for you. So you can pull the 8 out front, and then the integral of e to the x is just e to the x. So you have your 8, e to the x, and you have to add a constant. Here, following the formula perfectly, right? If you take the derivative of this, you get your e to the 8 back, e to the 8t, and then you'd have to multiply by the 8. So that's why you have to divide the 8 out, because there's no 8s over here, right? Okay, and then this one, they have a big pile of stuff. E to the stuff, we're going to have an e to the stuff. The 3, we could just pull it out front. But since there's a 5/6 here, we're going to have to divide by a 5/6. Right, it's 6/6. All right. Point here. All right, we can pull out the -7, and the integral of e to the x is e to the x. We're going to need e to the 5x, but if I took the derivative of that, I'd end up with a 5, and there's no 5 over here. All right, e to the 4x, I'm going to need an e to the 4x, but if I took the derivative of that, I'd get a 4, and there's no 4 here, so I need that. And then the second part here, I have a -4, and the integral of e to the x is e to the x. This one, I'll pull out the -11, and then the derivative of e to the -x is e to the -x, but I'm going to have to divide out that -1. So we could write this simply as 11 e to the -x plus constant. Okay, so you have the 11 e to the -x, and then you get that extra minus. Oops. Can you handle these? They're too bad. The hard part is just practicing enough to where it's reflex. You can see that I can do this stuff without thought, right? At the beginning of the last class, I couldn't do it without thought. I was messing it up. Of course, my stomach was hurting like hell, but sit down for 5-10 minutes, get your brain percolating, and you should be able to do this reflexively. All right, so this is what I told you about the natural log. Okay, so the integral of x to the -1 is going to be the natural log, because the derivative of natural log is x to the -1. That's as far as I got in the last class, so I'm going to call it there. Y'all have any questions? Anything at all? All right. Have a good Halloween. Stay safe.